Have you ever opened a JavaScript project and felt overwhelmed by messy code, tangled global variables, and mysterious bugs that seem impossible to trace? Imagine building scalable, maintainable front-end features without battling naming conflicts or relying on heavy build tools. That's exactly what the JavaScript Module Pattern offers, a proven way to organize and encapsulate your code for clarity, safety, and rapid development, all using features built into every browser. In this tutorial, you'll discover how the module pattern can transform your approach to front-end architecture. You'll learn how to shield your internal logic from accidental interference, group related functionality into cohesive modules, and create reusable components that are easy to test and maintain. Whether you're prototyping, working within a legacy app, or embedding dynamic features into a CMS, mastering this pattern will streamline your workflow and safeguard your code from common pitfalls. The problem is clear: as your JavaScript grows, so does the risk of accidental conflicts, hard-to-find bugs, and code that's difficult to extend or debug. Without a solid structure, even simple projects become fragile and hard to manage. The module pattern solves this by giving you the power to control scope, expose only what's needed, and keep your global namespace clean. By the end of this session, you'll have practical strategies and step-by-step guidance to implement robust, modular JavaScript. No build tools required. If you want to write code that's portable, reliable, and ready for the demands of real-world apps, you're in the right place. For more in-depth tutorials and practical guides that keep you ahead of the curve, make sure to subscribe, stay updated, and let's build smarter, more scalable JavaScript together. Imagine a bustling city where every building is constructed without walls or boundaries. Rooms blend into each other, and anyone can walk in and rearrange the furniture. This chaos mirrors what early JavaScript development looked like. Every variable and function lived in the global scope, prone to accidental overwrites, naming collisions, and unintended side effects. The first core aspect of the JavaScript module pattern is encapsulation, the act of building solid walls between code units to protect their internal state and functionality from the outside world. Encapsulation in the module pattern is achieved using closures, a feature where functions remember the scope in which they were created. By wrapping code inside an immediately invoked function expression, IIFE, we create a private environment. Variables and helper functions declared inside the IIFE are invisible to the outside, while only selected methods or properties are exposed via a returned object. This is akin to a hotel with rooms accessible only via a front desk. Guests can request specific services, but cannot wander through staff-only corridors. For example, a counter module encapsulates the current count and all its logic. The outside world can increment or reset the count, but can't directly tamper with the counter's inner workings. This guards against accidental or malicious interference, greatly reducing bugs and making code easier to reason about. Encapsulation also leads to more predictable code, because each module's internal state can only be modified through its defined public API. This is the foundation upon which maintainable and scalable JavaScript applications are built, much like how strong walls and locks make for a secure and orderly city. Consider a library where every book shares the same title and author. Finding the right book would be nearly impossible. Early JavaScript suffered from a similar problem. All scripts dumped their variables and functions into a single global namespace. The second key aspect of the module pattern addresses this with namespace management. A namespace is essentially a labeled container, a way of grouping related code under a single unique identifier. By returning an object from an IIFE, the module pattern creates a namespace that bundles together related properties and methods, reducing the risk of name clashes. Instead of hundreds of global variables, you have a handful of well-named modules, each acting as its own bookshelf in the library, neatly organizing volumes by topic. For instance, in a web page with both a calendar widget and an analytics tracker, each can be encapsulated in its own module: calendar widget and analytics. Interactions with either feature happen through their respective namespaces. If both modules have an init method, there's no conflict. Each is accessed through its parent namespace, e.g., calendarwidget.init versus analytics.init. This clarity improves maintainability, makes debugging easier, and allows teams to work in parallel without stepping on each other's toes. Namespace management also makes your codebase more portable and composable, as modules can be moved, reused, or replaced without worrying about polluting or conflicting with the global scope. Think of a modular kitchen where each appliance, oven, dishwasher, fridge, has a dedicated function and can be swapped or updated independently. The third essential aspect of the JavaScript module pattern is reusability and composability. Well-designed modules are like these appliances, self-contained units that provide a clear interface and can be combined in various configurations to build increasingly complex systems. The module pattern encourages developers to break down applications into logical, feature-focused units. Each module exposes only what is necessary for the outside world, keeping its internal logic and state private. This means a tab navigation module, for example, can be embedded in multiple pages, or even in different projects, with minimal modification. Such modules are portable. They can be shared across teams or open-sourced for community use. Composability arises when modules interact via well-defined interfaces or shared event systems. Instead of tightly coupling modules together, they communicate through public methods or event buses, allowing for flexible and scalable architectures. If one module needs to be replaced or upgraded, it can be done with little risk of breaking the rest of the application, just like swapping out a kitchen appliance without rewiring the entire kitchen. This approach lays the groundwork for robust, adaptable codebases that can evolve as requirements change. Picture a complex machine where each cog and gear is custom-made for its place, but if you need to test or replace a single part, you're forced to take apart the entire system. In programming, this problem is known as tight coupling, when different parts of your code depend too heavily on each other's internal workings. The fourth pillar of the module pattern is dependency isolation. Dependency isolation is about minimizing the connections between modules. Instead of reaching directly into each other's internals, modules interact only through their public APIs. This separation means that changes inside one module do not ripple unpredictably through the rest of your application. For example, a logging module might be passed into a user module as a dependency, rather than the user module importing or accessing the logger via a global variable. This makes each module more testable, as you can swap in mock dependencies during testing, and more robust, as failures in one module are less likely to impact others. In practical terms, dependency isolation in the module pattern can be achieved by passing required objects as arguments to the IIFE or exposing only minimal hooks for interaction. This strategy results in code that is easier to maintain, extend, and debug, just as a well-designed machine allows you to update a single part without dismantling the whole apparatus. By isolating dependencies, the module pattern supports large-scale applications where complexity is managed through clear, controlled interfaces between components. Imagine a toolkit that's effective in both a high-tech workshop and a remote campsite, versatile, reliable, and unburdened by external requirements. The fifth aspect of the JavaScript module pattern is build tool independence and universal compatibility. Unlike ES6 modules or CommonJS, which often require transpilers or bundlers like Webpack to work across different browsers, the classic module pattern leverages only core JavaScript features, functions, closures, and objects. This means that modules written using this pattern run natively in any JavaScript environment, be it the latest Chrome, an older version of Internet Explorer, or a constrained embedded browser with no support for modern syntax. This independence from build tools is a significant advantage for projects where simplicity, speed, or legacy compatibility is a priority. It allows for rapid prototyping, easier embedding in CMSs or third-party platforms, and hassle-free integration in environments where introducing a build pipeline would be overkill or impossible. Developers can write, test, and deploy modular code directly, with no compilation step, no dependency on package managers, and no risk of build time errors. In this way, the module pattern serves as a universal toolkit for scalable front-end development, capable of meeting the needs of any project, regardless of technological constraints. Envision a well-run workshop where each tool is labeled, instructions are clear, and every worker knows which tools to use for which task. The sixth dimension of the module pattern is clarity of API contracts and maintainability. A module's public API acts as a contract with the rest of the application. It defines what can be done, what cannot, and how to interact with the module safely. By explicitly returning an object that lists all accessible methods and properties, the module pattern encourages developers to thoughtfully design and document these interfaces. This explicitness makes it easy for other developers to use modules correctly, reduces onboarding time for new team members, and makes future modifications safer. Furthermore, maintaining code becomes much simpler when the boundaries between modules are clear. Internal changes can be made with confidence, so long as the public API contract remains unchanged, like updating the engine of a car while guaranteeing that the pedals and steering wheel still work as expected. Well-structured modules also lend themselves to automated testing, as test cases can target the public API in isolation. This focus on contractual clarity and maintainability is what transforms code from a tangled web of interdependencies into a scalable, professional-grade system. Think of a garden where each plant is carefully pruned to encourage healthy growth, prevent overcrowding, and maximize yield. In modular JavaScript, the equivalent is performance optimization and resource management. The seventh perspective of the module pattern. While closures and encapsulation are powerful, they come with a cost. Excessive or careless use can increase memory consumption and slow down execution, especially in large-scale applications. The module pattern encourages developers to minimize the number of closures by grouping related functionality and avoiding monolithic, all-encompassing modules. Instead, code should be divided into focused, single-responsibility modules, each managing only what it needs. Performance can also be improved by caching frequently accessed resources like DOM elements within the module's private scope. Lazy initialization techniques defer expensive operations until they are actually required, further optimizing resource usage. By being judicious with encapsulation and vigilant about what is retained in closure scope, developers ensure that their applications remain efficient and responsive, just as a well-tended garden thrives with thoughtful cultivation and regular maintenance. Visualize a relay race where each runner passes the baton only when ready, ensuring smooth transitions and minimizing errors. The eighth principle of the module pattern is robustness in initialization and lifecycle management. Modules often need to set up internal state, attach event listeners, or interact with the DOM. By encapsulating this setup logic inside private functions, triggered through explicit initialization methods, modules ensure that all dependencies are in place before they start functioning. This guards against race conditions and unpredictable behavior, especially in complex apps where timing matters. Moreover, modules can implement cleanup routines within their API, allowing for graceful teardown, removing event listeners, nullifying references, and releasing memory when a feature is no longer needed. This lifecycle awareness is critical for long-lived applications, single-page apps, or any context where parts of the UI may be dynamically added or removed. Like a relay team coordinating each handoff, well-designed modules manage their own setup and teardown, contributing to the overall reliability and resilience of the application. Consider a team of chefs, each specializing in a type of cuisine, sharing a kitchen without interfering with one another. The ninth facet of the module pattern is inter-module communication and extensibility. While encapsulation keeps modules isolated, practical applications often require modules to cooperate. The module pattern supports this through well-defined communication mechanisms, such as shared event buses, or by passing references to shared services via dependency injection. This allows modules to remain decoupled, each chef focusing on their own dish, while still collaborating to deliver a complete meal. Extensibility is achieved by designing modules with extension points in mind. For example, a base module might expose hooks or allow additional behaviors to be attached via its public API. This means new features can be added without modifying the core logic, reducing the risk of regression bugs. As applications grow, this approach enables seamless expansion, accommodating new requirements without sacrificing the integrity or maintainability of existing code. The kitchen remains orderly, even as new chefs or cuisines are introduced. Imagine reading a novel where each chapter is written in a different language, requiring a translator at every turn. In software, this complexity is introduced when build tools or transpilers are needed for code to run across environments. The 10th and final perspective on the module pattern is comparative simplicity and agility. By relying solely on core JavaScript features, the module pattern eliminates the need for external tooling, configuration files, or complex build processes. This simplicity accelerates development cycles. Code can be written, tested, and deployed directly, with no waiting for builds or troubleshooting toolchain issues. The agility afforded by this pattern is particularly valuable for rapid prototyping, educational projects, or embedding features into systems where introducing a build pipeline is impractical. When compared to modern alternatives like ES6 modules, CommonJS, or AMD, the module pattern may lack certain features, such as static analysis or automated dependency resolution, but it excels in universality, speed, and ease of understanding. It empowers developers to focus on solving real problems rather than wrestling with infrastructure. In this way, the module pattern remains a timeless approach for agile, scalable JavaScript development, making modularity accessible in any context without translation or delay. This is the main JavaScript module file implementing the classic module pattern for a counter feature. The module encapsulates its internal state, exposes a clear public API, and demonstrates how to keep variables and helper functions private using an immediately invoked function expression, IIFE. This JavaScript file demonstrates how to utilize the counter module from the previous example within a web application. It binds DOM events to the module's public methods, allowing user interactions to manipulate the counter through an encapsulated API. This is the HTML file integrating the counter module and the application logic. It includes buttons for interacting with the counter and loads the necessary JavaScript files in the correct order to ensure the module is available when the app logic executes. This is a secondary module implementing the module pattern for tabbed navigation. It maintains private state for the active tab and exposes methods for initialization and switching tabs, ensuring encapsulation and isolated DOM manipulation. This HTML snippet shows how to set up tab content and controls, leveraging the tabs module's public API to switch between tabs without polluting the global namespace. This module implements a simple event bus using the module pattern, enabling decoupled communication between modules without direct dependencies. It supports registering event handlers and emitting events with associated data. This HTML test file uses vanilla JavaScript assertions to verify the correct behavior of the counter module. The tests check increment, decrement, and reset functionality, confirming encapsulated state manipulation via the public API. This code demonstrates the revealing module pattern, where internal functions are explicitly mapped to the public API. It provides methods for arithmetic operations and retrieving the total, maintaining encapsulation while improving clarity and refactorability. This example shows dependency injection in the module pattern by passing an external dependency, console object, into the module. It allows for greater flexibility and easier testing with mock dependencies. This Jasmine spec file provides automated unit tests for the counter module, validating increment, decrement, and reset methods. It is designed to be run with a Jasmine test runner in the browser. This is the Jasmine spec runner HTML file, which loads Jasmine's CSS and JavaScript, the module under test, and the spec file. Opening this file in a browser runs the tests with a visual results interface. This code demonstrates a namespaced module organization pattern, grouping related modules under a single global object to avoid global namespace pollution. It is especially useful for larger applications with multiple modules. The application opens with a tabbed interface displaying several navigation buttons and content areas. The initial view highlights the Tabs module, allowing users to see and interact with tabs labeled About, Features, and Help. Selecting the Features tab updates the content area to show information relevant to features, while selecting the Help tab switches the content area to help-related information. Returning to the About tab brings back the initial content. Next, the user navigates to the Counter section using the side navigation. The Counter module interface appears, showing the current count and buttons for incrementing, decrementing, and resetting the counter. The user clicks the Increment button 3 times, observing the count increase with each click. The Decrement button is pressed once, decreasing the count. The Reset button is then used to set the count back to 0, with the display updating accordingly. Switching to the To-Do List section, a To-Do application interface is presented. The user adds 3 to-dos by typing Read About JS Modules, Practice Module Pattern, and Build a Demo App into the input field, and clicking the Add button after each entry. The to-do list grows with each item. The user marks the first to-do as completed by clicking its completion toggle, which visibly updates the item's appearance. The second to-do is removed by clicking its Remove button, immediately deleting it from the list. The Clear button is then clicked to remove all remaining to-dos from the list, clearing the interface. Moving to the Analytics section, an analytics panel shows tracked events and actions. The user scrolls through the panel to view logged analytics data. Clicking the Clear button empties the analytics event log, providing a blank slate for future tracking. In the Settings section, various configuration options are available. The user toggles on Dark mode by checking its checkbox, causing the application's appearance to shift to a dark-themed color scheme. The Analytics setting is toggled off by unchecking its checkbox, disabling analytics tracking. Re-enabling analytics is accomplished by checking the box again. Returning to the Counter section, now with dark mode still enabled, the user observes the counter interface with the updated theme. Finally, navigating back to the Tabs section demonstrates that navigation remains smooth and all modules continue to function and display correctly, reflecting the current settings and state of the application. You've just seen how the JavaScript module pattern gives you the power to organize, encapsulate, and scale your front-end features without ever needing build tools or modern browser dependencies. This pattern is your ticket to writing cleaner, safer, and more maintainable code, whether you're working on a quick prototype, updating a legacy project, or building embeddable widgets for clients and teams. By mastering this approach, you can avoid messy global variables, prevent bugs before they start, and design components that are both robust and easy to test. The next step? Start modularizing your own scripts. Break out a feature and wrap it in a module, or refactor an old project to see the instant clarity it brings. Want to consistently level up your skills with practical patterns and real-world examples you can put to use right away? Subscribe now, because the fastest way to become a confident, in-demand JavaScript developer is by learning proven techniques like these, shown step by step, with clarity you won't find anywhere else.